Friends, welcome to the lecture of Advanced Discrete Mathematics. Today we will see what is an modular lattice. Okay. Okay. So first let us see what is an modular lattice. Okay. A lattice L mid join is said to be modular if A join B meet C is equal to A join B meet C whenever A precedes C for all ABC belonging to Yep. So any lattice L with operations meet and join is said to be a modular lattice if it holds this condition whenever A precedes C for all ABC belonging to lattice L. That is A join B meet C is nothing but A join B meet C. Whenever A precedes C for all ABC belonging to L. If the lattice holds this condition for all ABC in L, then the corresponding lattice is called a modular lattice. Okay. Now let us see some examples or results depending on modular lattice. Every distributive lattice is modular. Okay. So here we have to show that every distributive lattice is a modular lattice. Let us consider let L with relation precedes be a distributive lattice, and ABC are elements belonging to L such that A precedes this C. So here, as we have to show that every distributive lattice is a modular lattice, first let us consider L be any distributive lattice which is from the given statement, and ABC are any three elements belonging to L such that A precedes C. Now here, as we have to show that every distributive lattice is a modular lattice, then we have to prove that if we take any ABC belonging to this L, then it holds this condition. Okay. And again, here we have given that distributive lattice. Any lattice L with operation meet and join is said to be a distributive lattice if it holds the condition, that is A join B meet C is nothing but A join B meet A join C. That is, as L is a distributive lattice, A join B meet C is nothing but A join B meet A join C. Meet and join are unit two operations. This is from the distributive lattice since given that L is distributive. Okay. Now, as here given that A precedes C, then by the definition of this precedes A join C is nothing but C, since A precedes C, therefore A join C is nothing but C. Now put this value A join C in this one, then we get A join B meet C, which implies A join B meet C is equal to A join B meet C, and which is nothing but the condition of modular lattice. A join B meet C will be equal to A join B meet C whenever A precedes C. Therefore, if we take any distributive lattice, then it holds this condition, and if it holds this condition for any ABC belonging to L, then we say that this corresponding lattice is a modular lattice. Therefore, from this we conclude that every distributive lattice is a modular lattice, which implies every distributive lattice is modular lattice. Is modular. In previous lecture, we have already proved that every chain is a distributive lattice. As every chain is a distributive lattice and every distributive lattice is a modular lattice, which implies every chain is also a modular lattice. As every chain is distributive, which implies every chain is every chain is modular, which is from the transitive property. Okay, as every chain is a distributive lattice and every distributive lattice is a modular lattice, which implies every chain is a modular lattice. As here we have proved that every distributive lattice is a modular lattice. What about its converse? Whether every modular lattice is a distributive lattice or not? Actually, every modular lattice is not a distributive lattice. That is, converse will not be true. We will give one example in which the corresponding lattice is a modular lattice, but the lattice is not a distributive lattice, which implies we say that every modular lattice is not a distributive lattice. Okay, prove that the lattice given in the following diagram is modular. Okay. First, let us see the what should be in the diagram. So this one is the diamond lattice, and we have to prove that this diamond lattice is a modular lattice. In previous lectures, we have already proved that diamond lattice is not a distributive lattice. We know that diamond lattice is not a distributive since it does not hold the property of distributive lattice, that is a joint b mid c will be equal to a joint b mid a joint c does not hold in this given diamond lattice. Therefore this one is not a distributive lattice, and we have already seen in previous lecture. Now we have to check whether this one is a modular lattice or not, as the given lattice is symmetric about these three vertices, that is b1 b2 b3. It is symmetric about these three vertices. Therefore if we take this b1 as either we take b1 b2 or b3, any among these three. Now from this diagram there are only possibilities of 0 sorry b1 precedes 1 and 0 precedes b1. These are the only two possibilities for this diamond lattice. Either we will take b1 b2 or b3, since this lattice is symmetric about these three vertices b1 b2 b3. Therefore either we take b1 or b2 or b3. These two are the only possibilities. Therefore as now we have to check this diamond lattice is whether it is modular or not. For modular lattice we require this one condition, that is a precedes c. So here there are two possibilities for a and two possibilities for c. From this one, what should be the values of a? Either b1 or 0. And what should be the values of c? Either 1 or b1. For this one, c is nothing but 1 and a is nothing but b1, and this one c is nothing but b1 and a is nothing but 0. Now here we have to see the both the cases. First we will see for this one, and secondly we will see for this one. Okay, in first case 1, let a is equal to b1 and c is equal to 1. Now here we get this one condition, that is such that condition for all ABC belonging to L. Now it remains to check whether this condition will be satisfied for this lattice or not, that is for this A and C. Consider A join B mid C is equal to, A is nothing but B1 join B is as it is mid C, C will be 1, which is equal to B1 join whatever will be the value of B, as 1 is the greatest element, B mid 1 will be B always, since if B is equal to 1 then it is B only. So, and if b is less than 1, that is b precedes 1, then b meet 1 is nothing but b itself. Therefore, as 1 is the greatest element, b meet 1 is nothing but b. Therefore, a join b meet c is nothing but b1 join b. And a join b meet c is equal to a is nothing but b1 join b meet 1. Now, whatever will be the value of b1 join b, as 1 is the greatest element, b1 join b meet 1 is nothing but b1 join b. b1 join b. Therefore, from 1 and 2, as RHS will be equal, then LHS must be equal, which implies a join b meet c is equal to a join b meet c. Therefore, for this a and c, this one is a modular lattice. Now it remains to check whether for this a and c is a modular or not. Okay, let us take second condition. Case 2. Let a is equal to 0 and c is equal to b1. Okay, consider a join b meets c is equal to 0 join b meet c. B is as it is, meet b1, which is equal to 0 join anything is that anything, that is b meet b1. Whatever will be the value of b, and a join b meet c is equal to a is nothing but 0 join b meet, sorry, 0 join b meet b1, 0 join b and meet b1, b meet b1. So again, from this 3 and 4, the RHS will be equal, then LHS must be equal, which implies a join b meet c is equal to a join b meet c. Whatever will be the value of b, whatever b value of this b, for this one a join b meet c will be equal to a join b meet c. This one is true in both the cases, and these are the only two possibilities for values of a and c. Therefore, from this we say that this given diamond lattice is a modular lattice, as it holds the both the cases. Therefore, the given diamond lattice is a modular lattice. But as this one is not satisfies the condition of distributive lattice, therefore this one is not a distributive lattice, but this one is a modular lattice. So here we get one example in which the given lattice is a modular lattice, but it is not a distributive lattice. Hence, every distributive lattice is a modular lattice, but converse need not be true. And for that, this one is the example. Okay. Here we have to prove a result, that is the pentagonal lattice is not modular. So here we have to prove that the pentagonal lattice is not a modular lattice, which implies, now let us draw one pentagonal lattice. Okay, this one is 0, A1, A2, A3 and 1. So now we have to prove that this pentagonal lattice is not a modular lattice. Okay, to prove that this lattice is not a modular lattice, then we have to prove that a join b meet c is not equal to a join b meet c for some ABC belonging to this lattice L. Okay. So let us consider value of A is equal to A2, value of B is equal to A3, and value of C is equal to A1. Here we have to choose these values in such a way, since for modular lattice we require the condition A precedes C. If we take the values of A equal to A2 and C equal to A1, then from this we clearly say that this A2 precedes A1, that is A precedes C. Hence we have to take the choice of values of A, B, C in such a way. Okay. So now here clearly A precedes C, since A2 precedes A1 in this lattice. Okay. Now here let us consider A join B meets C. Value of A is nothing but A2, join B is nothing but A3, meet C is nothing but A1, which is equal to A2 join. A3 meet A1. A3 is here and A1 is this one. Then its meet value is nothing but 0. And A2 join 0 is nothing but A2. Okay. And A meet, sorry, A join B meet C is equal to A is nothing but A2 join A3 meet A1. A2 join A3, from this diagram A2 join A3 is nothing but 1. Meet A1, as 1 is the greatest element, 1 meet A1 is nothing but A1. Therefore from equation 1 and equation 2, right hand sides are not equal, therefore left hand side must be not equal, that is as A1 is not equal to A2, which implies this one is not equal to this one, therefore it does not hold the condition of modular lattice. Therefore the given pentagonal lattice is not a modular lattice, since here we get the values of ABC for which the given condition of modular lattice will be not satisfied. Hence the given pentagonal lattice is not a modular lattice. Okay. From this one there is one result. A lattice, there is one result. A lattice L meet join is modular lattice or is said to be modular if and only if it does not have a sublattice which isomorphic to, that is isomorphic to pentagonal lattice. So any lattice L with operations meet and join is said to be a modular lattice if that lattice does not have a sublattice which isomorphic to a pentagonal lattice. Then only we see that the corresponding lattice L is a modular lattice. Okay. Now next one. If L meet join is a complemented distributive lattice, then De Morgan's laws A join B is nothing but A dash meet B dash and A meet B dash is equal to A dash join B dash holds for all A comma B belonging to lattice. So, if your given lattice L is a complemented distributive lattice, then we have to show that the corresponding lattice in that corresponding lattice, the De Morgan's law holds, that is A join B dash. That is complement of A join B is nothing but A complement mid B complement, and complement of A mid B is nothing but A complement join B complement. That these two conditions we have to prove. As here given that L is a complemented distributive lattice. Complemented distributive lattice. Okay, as this one is a complemented distributive lattice, then it is both complemented and distributive lattice. And any lattice is said to be a complemented lattice if it is a bounded and every element in L has a complement. Then we say that the corresponding lattice is a complemented lattice, which implies L is bounded. L is bounded. And in distributive lattice, there is one result. If the lattice L is a distributive lattice, then the complement of every element is unique. And here L is bounded and complement of every element is unique. Complement of every element is unique. Okay, this L is bounded, which is from the definition of complementary lattice. Since any lattice is said to be complemented, if it is bounded, and complement of every element will be exist, and complement of every element is unique, which is from the distributive lattice. If L is any distributive lattice, then there is one result: the complement of every element will be unique. Now, as here we have to prove that A join B complement is nothing but A complement with B complement. As to prove this one, A join B complement is nothing but A complement B complement, A complement intersection B complement. It is similar to prove that A complement with B complement is complement of this element A join B. As to prove A complement with B complement will be equal to A join B complement is similar that this A mid B complement is the complement of A join B, and if A and B are any two elements in any lattice L, then B is said to be a complement of A if A join B is equal to 1 and A mid B is equal to 0. Then we say that this B is a complement of A. And we have to prove that this A complement in mid B complement is the complement of A join B. Then we have to prove that A join B join A complement mid B complement is equal to 1 and A join B mid A complement mid B complement is equal to 0. Then we say that this A complement mid B complement is the complement of A join B, and from this one we say that these both are equal. Okay, now consider A join B join A dash, that is A complement with B complement is equal to, now A join B join A dash, A join A dash meet A join B meet, sorry, A join B join B dash. Okay, so this one can be written as A join A dash join B meet A join B join B dash. Okay, now this is the question. A join A dash, as A dash is a complement of, therefore A join A dash is nothing but the greatest element, which is 1. 1 join B meet A join B join B dash 1, which is nothing but 1 join B is nothing but 1 meet A join 1. Again, as 1 is the greatest element, A join 1 is 1 and 1 meet 1 is 1. Therefore, here we have proved that A join B join A dash meet B dash is nothing but 1. Now, second one, and A join B meet A dash meet B dash is equal to A meet A dash meet B dash is join B meet A dash meet B dash, and this one can be written as A meet A dash meet B dash join A dash meet B meet B dash. As here A dash is a complement of A and B dash is a complement of B, then A meet A dash will be equal to 0 and B meet B dash will be equal to 0, which is equal to 0 meet B dash join A dash meet 0, and as 0 are the lowest element, that is least element, therefore 0 meet B dash is 0, join A dash meet 0 is 0, which is equal to 0. Therefore here A join B join A dash meet B dash is equal to 1 and A join B meet A dash meet B dash will be equal to 0. Therefore A dash meet B dash is the complement, it is behaves as a complement of A join B, since if for any two elements A and B is said to be a complement of A, if A join B will be equal to 1 and A meet B will be equal to 0, then we say that the element B is a complement of A. As here A join B join A dash meet B dash will be equal to 1 and A join B meet A dash meet B dash will be equal to 0. Therefore this one is behaves as a complement of A join B. But as given lattice is a distributive lattice, therefore complement of every element is unique. Therefore A dash meet B dash is only the complement of A join B. As this one is the only the complement of this one, which implies A join B complement is nothing but A dash meet B dash. Similarly, we can prove that A meet B dash is equal to A dash join B dash. Okay, and hence the proof. Okay, now let us see next result. In turn, show that in a complementary distributive lattice, the following is V valid. First one, this is C. Second one, A is B dash equal to 0. Third one, A dash will be equal to 1, and fourth one, B dash is 6. B dash. Now, if your given lattice L is a complementary distributive lattice, then we have to prove that the following these four statements are equivalent. That is, if A precedes B, A precedes B, A meet B dash will be equal to 0, A dash and B will be equal to 1, and B dash precedes A dash. If L is a complementary distributive lattice, then these four statements are equivalent. And how will you prove these four statements are equivalent? That is, first we will prove 1 implies 2, 2 implies 3, 3 implies 4, and 4 implies 1. Then we say that these four statements are equivalent. So its solution is nothing but, in first case we will prove 1 implies 2. As we have to prove 1 implies 2, then let us consider A precedes B. As A precedes B, which implies A join B is equal to B. Since A precedes B, therefore, which implies A join B meet B dash is equal to B meet B dash. But we know that B meet B dash is nothing but, as B dash is a complement of B, B meet B dash will be equal to 0, which implies A join B meet B dash is equal to 0. Now, this one is nothing but A meet B dash join B meet B dash. and which is equal to 0, which implies A meet B dash join. Again B meet B dash is 0, which is equal to 0, and A meet B dash join 0 is nothing but A meet B dash, and which is equal to 0, and which is the second statement, which implies from this we say that 1 implies 2, therefore 1 is implied by 2. Now in second condition, let us consider this one. A meet B dash is equal to 0, which implies, let us take complement on both sides. Then we get A meet B dash complement is equal to 0 complement. Complement of 0 is nothing but 1, which implies, and according to De Morgan's law, A meet B dash complement is nothing but A dash join complement of B dash. So complement of B dash is nothing but B, and which is equal to 1. Therefore, A dash join B is equal to 1, which implies, we say that 2 implies 3. Okay, so here we have proved that 2 implies 3. Now, let us consider the third statement, that is A dash join B is equal to 1, which implies, again, let us take A dash join B meet B dash is equal to 1 meet B dash, as 1 is the greatest element, 1 meet B dash is nothing but B dash. Okay, now which is nothing but A dash meet B dash join B meet B dash is equal to B dash, which is equal to A dash meet B dash join B meet B dash, as B dash is a complement, this one is nothing but 0, which is equal to B dash, which implies A dash meet B dash is equal to B dash, and according to the definition of precedes relation, A dash meet B dash will be equal to B dash. It must imply that this B dash must precedes A dash. Therefore, 3 implies 4. Okay. Now it remains to prove that this one implies this one. Okay. Let B dash precedes A dash, which implies A dash meet B dash is equal to B dash. Now let us take the complement on both sides. A dash meet B dash complement is nothing but complement of B dash is nothing but B, which implies, according to De Morgan's law, complement of A dash is nothing but A join complement of B dash is nothing but B. A join B is equal to B. Again, by the definition of precedes, A join B will be equal to B, which implies A precedes B, which implies fourth one implies 1. So here 1 implies 2, 2 implies 3, 3 implies 4, and 4 implies 1. As 1 implies 2, 2 implies 3, and 3 implies 4, which implies these are the if and only statements. Okay. So from this we conclude that the given 4 statements are equivalent. Okay. Now let us see the next point, which is nothing but what is an finite Boolean algebra, and which is the last point of this unit. Finite Boolean algebra. Okay, we have to see what is a finite Boolean algebra. Let us see a definition. A complemented distributive lattice is called Boolean lattice. What is a Boolean lattice? A complemented distributive lattice is nothing but a Boolean lattice, and a algebraic system defined on defined on Boolean lattices. Boolean lattice is called Boolean algebra. What is an Boolean algebra? First, we have to see what is an Boolean lattice. A complementary distributive lattice is nothing but the Boolean lattice, and a algebraic system defined on Boolean lattice is nothing but the Boolean algebra. Therefore, we say that. Therefore, we say that the system. We say that the system B plus dot dash 0 1, or it is also represented by B plus dot dash, where plus dot and dash are join, meet and complement operations. Complement operations respectively is an Boolean algebra. Therefore, a lattice which is represented by or an algebraic system defined by B plus dot dash 0 1, or it is also denoted by B plus dot dash, where this plus is nothing but join, dot is nothing but meet, and dash is nothing but complement, and these are the three operations respectively, and this one is called as a Boolean algebra. For example, power set of yes with inclusion relation is an complemented distributive lattice. Is an complemented distributive lattice. As this one is the complemented distributive lattice, which implies, as this one power set of S with inclusion relation is a complementary distributive lattice, then by the definition of Boolean lattice, this power set of S with inclusion relation is a Boolean lattice. Therefore, hence, power set of S with union, intersection and complement is a Boolean algebra. Boolean algebra. Since power set of S with inclusion relation is an complemented distributive lattice, as it is a complemented distributive lattice, hence it is a Boolean lattice. And as we have defined the algebraic system on this Boolean lattice, then it is a Boolean algebra, where union, intersection and dash are nothing but the join, mean and complement operations respectively. Okay, therefore power set of S with inclusion relation is a Boolean algebra with these three operations. Okay, now a finite Boolean algebra, Boolean algebra is one with finite number of elements. Finite number of elements. If a Boolean algebra contains finite number of elements, then it is called finite Boolean algebra. Therefore, there is one shortcut, that is a bounded, complemented and distributive lattice is known as finite Boolean algebra. Finite Boolean algebra. Okay. Therefore, a bounded, complemented, and distributive lattice is called as finite Boolean algebra. Therefore, if S is a set with n elements, then power set of S with inclusion relation is a bounded complemented maintained distributive lattice. Distributive lattice. As power set of S with inclusion relation is a bounded complemented distributive lattice, which implies power set of S with inclusion relation is a finite Boolean algebra. Right? Boolean algebra. Okay. Now there is one note or there is one result. From this we can easily check whether the corresponding lattices are the finite Boolean algebra or not. Important note that is every finite or a finite lattice is a finite Boolean algebra when algebra if and only if it is isomorphic to Bn for some positive integer n. Okay. So every finite lattice is a finite Boolean algebra if and only if the corresponding finite lattice is isomorphic to Bn for some positive integer n. And what is Bn? We have already seen in previous lectures of that is after the complemented lattice. B1, B2, B3. B3 is nothing but the number of digits which are from the binary digit 0 and 1 by taking 3 elements at a time. That is, for example, B3. B3 is nothing but B3 contains all the elements of the this type 0, 0, 0. 1 0 0 0 1 0 0 0 1 1 0 1 1 0 1 0 1 0 1 1 and 1 1 1. That is B3 is nothing but this type of elements. Therefore, Bn is nothing but which contains here elements of the type which are formed by the binary digit 0 and 1. Okay. Therefore, any finite lattice is a finite Boolean algebra if it is isomorphic to Bn for some positive integer n. There is one example. Show that D30 is a finite Boolean algebra. Finite Boolean algebra under partial order of divisibility. Okay, so here we have to show that D30 is a finite Boolean algebra under partial order of divisibility, and we know that what should be an D30? D30 contains all the elements which are the divisors of this 30. That is 1, 2, 3, 5, 6, 10, 15 and 30. Therefore, D30 contains 8 elements. Okay. Since we have already know that what should be D30, D30 contains all the elements which are the divisors of this 30. Okay. Now, as we have to prove that this D30 is a finite Boolean algebra, if we have proved that this D30 is isomorphic to some Bn for some positive integer n, then clearly we say that D30 is a finite Boolean algebra. Let us define a function. Define a function f from D30 to B3 such that, or defined by, B3 also contains 3 elements such that f of 1 is equal to 0 0 0, f of 2 is equal to 1 0 0, f of 3 is equal to 0 1 0, f of 5 is equal to 0 0 1, f of 6 is equal to 1 1 0, f of 10 is equal to 101, f of 15 is equal to 011, and f of 30 is equal to 111. So here we have defined one function f from D30 to B3 such that f of 1 is nothing but 0, 0, f of 2 equal to 1, 0, and so on, f of 30 nothing but 1, 1, 1. And we know that what should be an Hasse diagram of B3. As we have to show that this D30 is isomorphic to B3. Or first let us find out the Hasse diagram of D30. To draw the Hasse diagram of D30, just here we have to replace the corresponding pre-images of Hasse diagram of B3. But that for that we have to first know how to what should be an, that is what is the structure of Hasse diagram of B3. We have already seen this. Hasse diagram of B3 is nothing but this thing. This one is the element 0, 0, 0. Here there are three elements. Here is 1, 0, 0. This one is 0, 1, 0, and this one is 0, 0, 1. And for Hasse diagram, we will have to join this one. After that, here is one element, that is next element will be here. This one is the 1, 1, 1. Okay. Now this one will be 1, 1, 0, 1, 0, 1, 0, 1, 1. Okay. So this one is the Hasse diagram of this one is the Hasse diagram of B3. Okay. Now to find out the Hasse diagram of D30, just we have to replace the corresponding pre-images of Hasse diagram of B3. Therefore, according to this one, Hasse diagram of D30 is nothing but, as pre-image of 0, 0, 0 is nothing but 1. So sorry, 1. So here is 1. Here there are three elements. Again there are three elements, and here is one element. So okay, so 1, 0, 0, 2, 0, 1, 0, 3, 0, 0, 1, 5, 1, 1, 0, 1, 0, 1, 0, 1, 1, and sorry, here 1, 1, 0 is 6, 10, 15, and 30. So this will be the Hasse diagram of D30. As according to graph theory, as these two Hasse diagrams are isomorphic, therefore D30 is isomorphic to B3. Since Hasse diagrams of both D30 and B3 are same, therefore as these two Hasse diagrams are same, then D30 is isomorphic to D30 is isomorphic to B3. And according to this result, a finite lattice is said to be a finite Boolean algebra if it is isomorphic to some Bn for some positive integer n. As D30 is isomorphic to B3 and 3 is a positive integer, which implies D30 with relation divisibility is a finite Boolean algebra. Finite Boolean algebra. Okay. Again, there is one result on Dn, the result for Dn. If n in Dn be written as n equal to p1 into p2 into up to so on pk, where pk's are distinct primes, then Dn is a finite Boolean algebra. Finite Boolean algebra. Okay. So here we have to see the examples. This one is the result. If n in Dn, that is the n in Dn can be written in this form, that is n equal to p1, p2 up to so on pk, that is the product of k distinct primes, that is if the n can be written as the product of k distinct primes, then the corresponding Dn is said to be a finite algebra. Okay, and if it cannot be written in this form, then the corresponding Dn is not a finite Boolean algebra. Example: determine whether B12 is an a finite Boolean algebra or not. Finite Boolean algebra or not. Okay. Therefore, here as values of n will be equal to 12. So here given that n equal to 12. Let us write this n as 2 into 2 into 3. Therefore 2 into 2 4, 4 into 3 12. But here n cannot be written as a product of distinct prime, since here the prime 2 will be repeated. Therefore, which implies D12 is not a finite Boolean algebra, since D12 12 cannot be written as a product of distinct primes. For example, let us consider for D30. If we consider for D30, therefore n equal to 30, and this 30 can be written as 2 into 15, 2 into 15 30, that is 2 into 3 into 5. Therefore, D30 can be written as a product of three distinct primes, 2, 3 and 5. Therefore, from this result, D30 is Boolean, finite Boolean algebra. Similarly, we can check for any Dn. Okay. So here our chapter posset and lattices will be completed, and so the as finite Boolean algebra is a last point of your possets and lattices. Therefore, here our syllabus of whole advanced discrete mathematics will be completed. Thank you for watching the lecture.